Good morning, everybody. I'm going to give everyone just a minute to get connected here, and then we'll go ahead and get started probably in about 3 minutes. So if you haven't had a chance yet, go ahead and start looking at these first couple of problems. See if you can come up with a valid Lewis structure, but we are going to ignore this first one. Okay. So try number 2 and number 3, and we'll get going in just a minute. All right, before we get started, are there any questions anyone had in preparation for this? Any concerns, questions about the exam, anything I can help with? I am trying to figure out the recording. I've never done it before. I am recording the meeting. I'll have to figure out how to get that posted and everything. So I'm going to try my best to get the recording posted, but I can't guarantee anything. I'm not sure how it works. So I am recording it, and I'll try to figure that out. Any other questions? Feel free to unmute yourself as well if you have a question. If there is any calculations, it'll be something you could do without your calculator, pretty basic math. Shouldn't be anything too crazy though, if there's any calculations. I don't think there's any math stuff in exam 1. So, good question though, thank you. The only thing you'll be doing with pKa or Ka is determining which one's larger, and then comparing if it's a stronger or weaker acid, so you won't have to do any calculations with those for this exam. You got it. Any other questions? Okay. I am going to turn my video off because it makes it easier for me to write on my computer. So hope that's okay with everybody, but let's go ahead and get started here. All right, so questions like number 2, I usually like to start with a carbon chain and then add on any other atoms besides, hydrogens basically, and then see where we're at that point, okay? So I'm gonna start with a 4 carbon chain. Okay, and then let's say we add our oxygen right here, okay? So let's write it like this as it is, okay? Now we need to add hydrogens, and we know the molecule is not negatively charged. So let's add a hydrogen on here. And then let's count how many hydrogens we have left. So there'd be 2 here. 2 here, 2 here, and 3 here. Do we have too many hydrogens? Yes, right? Because we're only supposed to have 8 hydrogens. And here we have 3, 4, 5, 6, 7, 8, 9, 10. We have too many hydrogens. Okay, so let's try something a little different. We have our carbon chain with 4 carbons. Okay, why don't we add the oxygen right here, and let's try this as an OH group like that. Okay, so now we'll count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still too many. So why don't we try a double bonded oxygen? Let's try a C double bond O. Count how many hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So now we have 4 carbons, 8 hydrogens, and 1 oxygen. So this would be our valid Lewis structure. Did anyone come up with any other answers other than this?
Yeah, I got the carbon chain, and then I just got a double bond of oxygen at the end.
Something like that?
Yeah.
Okay. So that'd be 1 hydrogen, 2, 3, 4, 5, 6, 7, 8. Perfect. Yep. That is another option here. What functional group is this? Does anybody know?
Not too good.
That's right. Close. It looks a lot like a carboxylic acid. Okay, carboxylic acid would look like this with an OH instead of just an H. Okay. Yep, perfect. Tanner got it. It's an aldehyde. Okay. So when there's no OH right here, if this was an oxygen, it would be a carboxylic acid, but since it's just a hydrogen, it makes an aldehyde. Awesome. How about what's the functional group here? Any ideas? All right, this is a ketone. We'll talk a lot more about functional groups here in just a bit. I'm pretty sure I covered all the ones he wants you to know in the examples I give you, so we'll talk about all those and go from there. Okay, let's try number 3. So again, I'm going to start with a carbon chain, and this time we only have 2 carbons. So it's going to be something like that, and we have 2 oxygens. Okay, so just thinking through this, the only way to really add 2 oxygens onto here is to have a double bond, right? Because we have very few hydrogens and 2 whole oxygens. So let's try something like a double bond. And then maybe we can add an OH over here. Okay. So then we have a hydrogen here, 2 here. And that gives a total of 4 hydrogens, 2 oxygens, and 2 carbons. Okay. So that looks good to me. The other way to do this is to have something like this. Okay. So we have our 2 carbons, 2 oxygens, and 1, 2. Oh, that doesn't give us enough hydrogens. No, it does. We're good. 4, 5. Yep. Perfect. Any questions on those? On 2 or 3. Any questions?
I do have a question.
Yeah, go ahead.
I had a little harder time getting 3 because it's just like kind of hard managing the oxygen and figuring out. I guess just asking if there's like different patterns you can use to try to identify or like see different things. The best I got is like I just know that oxygen always has 2 bonds. and that's
Yeah.
as far as I can probably go. And then from there, just kind of like trial and error.
Yeah, from there, probably trial and error. You can pretty much assume usually carbon and oxygen bonds like to be double bonded together. So if you're having a hard time putting it together, try a C double bond O. Otherwise, it'll probably be an OH, or maybe you could have a carbon, oxygen, carbon, something like that, which that's an ether, right? But then, you'd obviously have to add like your OH down here. I'm trying to think, 1, 2, 3, no, it'd be too many hydrogens. So that wouldn't work for this particular problem, but just trying different patterns like that, because carbon, oxygen like to be double bonded. That's a common one that Dr. Garg especially likes. He especially likes carboxylic acid problems when he gives you the chemical formula, and then you have to draw the structure. So if there is 2 oxygens, try adding a carboxylic acid. Just some different tips there.
Okay, perfect. Very much.
When we need to add any lone pairs when doing these on the test, he's not going to have you draw anything because it's all multiple choice. So he's going to have different options, and you have to make sure that it is a valid structure. And usually with a skeletal structure like we've drawn here, you do not have to add lone pairs. Does that answer your question, Sophia?
Yes, it is.
Awesome. Any other questions? All right. So now we need to write the electron configuration for the following atoms and how many unpaired electrons in each, okay? So let's start with the electron configuration. Did he go over this with you guys? Was this a topic he's covered?
Mm-hmm.
Okay.
Yes.
Does someone want to either type or say what they got for this one?
Yeah, I'll do it.
Go for it.
1s2, 2s2, and then this next part I wrote both ways. I wrote 2p5, but I also put 2px2, 2py2, and then 2pz1.
Perfect.
I was wondering, yeah, which well, I guess you said it's multiple choice, so.
Yeah, he is going to write it 2p, x, y, and z in that configuration. He wants you to know it that way. So it'll be 1s2, 2s2, 2px2, 2py2, 2pz1. Okay. Awesome. Let's try the chloride ion. Okay. So we're going to start off very similarly. Okay. First of all, what do you guys know what the atomic number is for chlorine?
17.
It is 17. Perfect. Okay. So Cl minus means that it has one more electron. So we know there's going to be 18 electrons total that we need to account for. Okay. Because it has a negative charge. We need to account for 18 electrons. So we're going to go 1s2, which is 2, 2s2, 2px, 2py, 2pz. Do we have enough electrons to fill all of these p orbitals?
Yes.
Yes, we do. Okay, so 2px2, 2py2, 2pz2. Then we move on to 3s2. Let's see, 1s2, 2s2, yeah, 3s2. And then 3px, 3py, and 3pz. Okay, so far we have, let me mark them like this: 2, 4, 6, 8, 10, 12. So we still need to account for 6 electrons to get to our 18 number. So are the 3p shells all going to be filled?
Yes.
Yes. Okay, so we're at 2px2, 3py2, and 3pz2. Awesome. Let's go ahead and try boron. Does anyone know what the atomic number for boron is? I'm gonna have to go look it up. I can't remember. All right, boron is atomic number 5. Okay. So we have a total of 5 electrons we need to account for. So we're gonna go 1s2, 2s2, and then 2px, 2py, 2pz. Okay, so far we've used 4 electrons. So what's going to happen in our p shells? How many electrons?
Just one.
Just one in our p shell, right? Okay, and it's always going to go on the x first. Okay, so we're going to have 1 here, and then because we have no more electrons, either he's going to ignore 2py and 2pz and not even write them, or he'll write them with zeros. Okay, just not sure which format he's going to put it in, but making you aware of both of those options. All right, so next we've got sulfur. Okay, sulfur has an atomic number of 16, and yes, he is going to give you a periodic table on the exam. Okay, so we need to get 16 electrons. So 1s2, 2s2, 2px, 2py, 2pz. We do have enough electrons to fill this shell, so we're going to go 2, 2, and 2. Then we go 3s2. Now we need to do our 3px, 3py, 3pz. Okay. So far, we've used a total of 2, 4, 6, 8, 10, 12. And we were trying to get to how many again? 16, right? Okay. So we're at 12, we need to get to 16, we need to have 4 more. So what we do here is we fill each one once, and then if we have extras, we go back and fill it again. So 3px1, 3py1, 3pz1, and we have 1 more electron we need to account for, so then 3px becomes 2. Does that make sense to everybody? Is there any questions on that one? All right, moving on. Oh, will you post the recording? I did address this quickly at the beginning, but I am recording it. I'm not sure how that works, but I am going to try my best to post the recording. I don't know how that works with Zoom and where it gets recorded to. I have no idea. So I will try my best afterwards to get this posted. All right, let's define a chemical bond. So does anyone have a good definition for a chemical bond?
If you think in terms of it fully restored, you're just seeing the beginning.
No definitions of a chemical bond?
Oh, sorry, I just got up. Okay, I'd say a chemical bond is an attraction of 2 atoms, whether it be opposite charges or sharing of electrons.
Yeah, that's a great definition. A simplified version would just be sharing of 2 electrons between atoms, right? It's 2 atoms that are sharing electrons so that they can both be happy and uncharged. Okay.
Mm-hmm.
So sharing of 2 electrons between atoms. Perfect. And something I just thought of as far as the recording goes, I'll definitely be posting this key. And so if the recording doesn't work, at least you guys will have access to the key. Okay. All right, we need to calculate the formal charge for the following atoms. How many electrons does oxygen want to have? Does anybody know? 6, right? Okay, and when we're talking about formal charges, we always want to account, bonds only count as 1 electron. Even though there's 2 electrons there, they're being shared like we talked about in the definition of a chemical bond. So there's 2 electrons in this bond, and we're only going to count oxygen owning 1 of them. Okay, so how many electrons does oxygen own right now?
7.
It owns 7, right? So it wants 6, and it owns 7. That gives us a formal charge of -1. Okay, so this oxygen will have a negative charge. Does that make sense to everybody? So we always want to do how many number of electrons it wants minus the number of electrons it has. Gives us your formal charge. All right, let's talk about nitrogen. How many does nitrogen want?
5.
5, right? Okay, so it wants 5. And how many does it have?
6.
6, right? Has 6, so that's going to give us a -1. This has a negative charge on it. How do we know how many electrons an atom wants? How do we know that number?
I looked at the periodic table.
Yeah, so it's based on the period that the atom is in. So if it's in the 6th column or 16th column, I guess, like oxygen is, okay, it wants 6 electrons. Okay, nitrogen is in the 5th column, so it wants 5 electrons. Okay. How about carbon? How many does carbon want?
4.
4, right? And how many does it have?
5.
It does have 5, so 4 minus 5 gives -1. I apologize, these are all negative so far. Let's talk about this last one. How many does oxygen want again? It wants 6, right?
Mhm.
And right now it has 2 lone pairs and 3 bonds, gives us 5, so that gives us a +1 charge. So this is positively charged. Any questions on those?
Nope.
Pretty basic topic, but it will be tested, so make sure you know it. All right, what is a constitutional isomer?
I put it's a different structural rearrangement of atoms for the same chemical compound.
Perfect. So same formula, right? Different connectivity. So there's different arrangements of atoms within a molecule. Okay. So we want to draw 2 constitutional isomers of the following molecular formulas. So we want to find out 2 different ways that we could make this formula, right? So we want to turn this into a structure. So like I said with these, I always try to start with our carbon chain. So we have 2 carbons, we'll just start like that. Okay. We have 1 oxygen and 6 hydrogens. So let's just we'll try a double bonded oxygen here. Okay. So this gives us 1 hydrogen here and 3 here. Okay. That only leaves us with 4 hydrogens, so that's not going to work. Okay. So again, we go back to the drawing board and say, well, let's not make it a double bonded oxygen, let's make it a single bond. That becomes an alcohol group, so that's 1 hydrogen, 3 hydrogens, 6 hydrogens. So that one will work. So we have CH3, CH2OH. Okay, that's kind of the order they go in. All right. So that's one of them. We need to draw another one. Did anyone come up with another structure?
Yeah, I go where the CH3 is on the outside and oxygen's in the middle.
Perfect. So we've got CH3O, CH3. Okay, so that gives us our 6 hydrogens on the end, oxygen in the middle. What functional group is this?
And ester?
Close. It sounds like ester. It's called ether. Okay. This is an ether. And I'm going to talk about some memory cues to help with remembering some of these later on when we talk more about functional groups. But I just wanted to bring that up for a minute. Okay, so that's our two different structures here. So then CH3O, CH3. Okay. All right, let's try the second one. Again, I like to start with a carbon chain. 1, 2, 3 carbons. We'll add our fluorine on the end, and then we'll count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7. Perfect. Okay, so that's one of them. We can do that. Again, we'll start with our carbon chain. Now, if we were to add it to this side, what's the problem with doing that? It's identical to the other one, right? All you'd have to do is turn this one around, do a 180 turn, and it would be identical as the first. Okay, so we don't want to do that. So let's try putting fluorine on the second carbon, okay, carbon number 2. All right, so then we count the number of hydrogens, 1, 2, 3, 4, 5, 6, 7. Perfect. Any questions on those? Awesome. So now we're going to talk about resonance structures, and we'll draw the hybrid for the molecules as well. And then if there is a major and minor, we're going to label it. All right, so how I like to approach resonance structures is I like to say, what's unhappy and how can I fix it? Okay, so what's unhappy in this molecule?
The nitrogen.
Nitrogen, right? No atom, no matter how electronegative it is happy holding a charge, okay? Holding that negative charge. They would rather be in the neutral state. So nitrogen is unhappy as it is right now. Okay. So what can we do? If we were to move electrons towards nitrogen, what would that do? It would make it what? Make it more negative, right? Okay. So we don't want to do that. So we want to move electrons away from nitrogen. So since it has lots of lone pairs, let's try and move one of these lone pairs and form a double bond right there. And what do we need to do in response to that move? Yeah, this carbon, if it gets another double bond right here, its octet would be broken. So we need to remove this double bond in order to make this carbon remain happy. Okay. So then we draw what happened here. We have this nitrogen, which has one lone pair, double bond, oxygen, which now has a negative charge, and hydrogen. Okay. And now the nitrogen has 5 electrons, so it's now neutral, and the oxygen is negative. Okay. All right, is there anything else? So now we look at oxygen, we say oxygen's unhappy. Is there anything we can do to make it happy that wouldn't just undo what we just did? Right, does that make sense? So without undoing what we just did, can we change anything about oxygen to make it happy? No, okay. There's nothing more we can do to this molecule to change it, to move the electrons around other than going straight back to where we were. Okay. So now we're going to talk about these two structures. Which one do you think is more stable, the original or our resonance?
One on the right. Going with a negative on the oxygen.
Perfect. So this is our major product. What makes this one major? What do you guys think the difference is?
The oxygen is more electronegative, so it makes it more ready to hold that negative charge.
Perfect. Oxygen is more electronegative, so it's capable of holding that negative charge better than nitrogen. So this would be our minor product. Okay. So now we want to draw a hybrid. Okay. Hybrids look kind of crazy, but once you kind of get the hang of it, it's not too bad. Okay. So all we want to do is draw our basic structure with no lone pairs, no double bonds, okay, just our base structure with single bonds, no lone pairs, no charges, anything, okay? So this is our base structure right here, okay? Now, we need to go through and write the minimum amount of lone pairs or double bonds that there was, okay? So on either one of these structures, okay, how many lone pairs, what's the least number of lone pairs that oxygen held in both of the structures? How many sets of lone pairs? Let's see, we had a question. So we don't break oxygen's octet rule? No, because oxygen still has 8 electrons around it, okay, which is the octet rule, but it has a negative charge. So that's not breaking the octet rule for oxygen. Does that answer your question? No, you're good. No worries at all. All right, so here oxygen had 3 sets of lone pairs, right? Whereas over here it only had 2 when it's in its neutral form. Okay, so we're going to draw the minimum number of lone pairs, which is 2. Okay, now let's do lone pairs for nitrogen. Here it had 2 sets of lone pairs. Here it only has 1, so we're only going to draw 1 set of lone pairs on the nitrogen. All right. Okay. There was not always a double bond between the carbon and the nitrogen. Okay, but because there was at one point, we need to draw a dotted line. Okay, because there is sometimes a double bond, there is sometimes just a single bond. Okay, so that's going to be a dotted line. The same goes between the carbon and the oxygen. Okay, there isn't always a double bond, but sometimes there is, so we need a dashed line there. All right. Now the last thing to talk about is charges. Okay. Here we have a negative charge on nitrogen, and here it's neutral. So that means we need to draw a partial negative next to that nitrogen. Same goes for oxygen. There was a negative charge here, but no negative charge here, so that's a partial negative charge on the oxygen. That's how you draw your hybrid. Any questions on that one?
Yeah, I have a question. When it comes to being like really picky about it, does it matter which side that dotted line is on?
Nope.
Oh, okay.
It does not. All right. Let's talk about the second one. Again, I like to first start off with what's unhappy and how can I fix it. So our oxygen is unhappy here, right? And if we were to move electrons away from the oxygen, it would become more positive. Okay, so we don't want to do that. We want to move electrons towards oxygen in order to make it happy. Okay, so we have a set of lone pairs here in this double bond, which we can move out onto this oxygen. Okay, so that's making oxygen more negative, which it wants to be. So then our resonance structure will be something like this, with 2 sets of lone pairs. Oxygen now has 6 electrons around it, so he's happy. What else do we need to add to this structure?
Carbon.
Because there's 7 hydrogens, 6. I always try to write out the formula too, so I remember if I still have the same amount of hydrogens and all that.
Yeah, for sure. So how many hydrogens were up here?
That's 7.
Okay. How about at this particular carbon? Just 1, right?
Oh, yeah, just 1.
Yep. So now this structure still only has 1 hydrogen. Okay. So that carbon right there only has 3 bonds and no lone pairs. So again, carbon wants 4 and only owns 3 electrons. So it's going to be +1. So there's going to be a positive charge left on that carbon. Again, probably the easier way to look at this is to say there was electron density here, and then we took the double bond away, and so now it's going to be more positive. And also the way you know you've done this right is if the formal charge stays the same in the molecule. Overall, there's still a positive charge in the molecule. you can go between like positive charge and neutral or negative charge and neutral, okay, but you don't want to go from a positive charge to a negative charge. Okay, so that's another check to make sure you've done this right. Okay. Again, we look at this molecule and we say what's unhappy and how can we fix it? Is there anything we can do to change this other than undoing what we just did? Okay, so carbon's unhappy, it has a positive charge, and there is a double bond capable of helping out. So this double bond could move up here. Okay, so now our molecule would look something like this. With a double bond here, oxygen now has that, and the positive charge would be here. Do you guys see how I did that?
Yes.
Nothing too crazy, all right? Again, resonance structures are scary, but all you need to do is follow the simple steps of what's unhappy and how can I fix it, and then make sure that your charge is correct throughout the molecule. Either it stays the same or it moves to neutral. Okay. All right, is there anything else we can do? This carbon down here is now positively charged. Is there anything we can do to it other than undoing what we already did to make it neutral? Is the one on the right more correct than the one in the middle? Okay, we're going to talk about that in just a second. Okay. So no other resonance structures, right? There's nothing else we can do to this molecule other than undoing what we did with our resonance structures, okay? So now we want to talk about major and minor products. All right, so which is more electronegative, first of all, oxygen or carbon?
Oxygen.
Oxygen is more electronegative, right? So carbon is happier holding a positive charge than oxygen, okay? So we're going to start here with when this oxygen has a positive charge, it's going to be our minor, okay? Our minor product, because over here a carbon holds the positive charge and over here a carbon holds a positive charge, okay? So that's our first clue here. Okay. So we know that's our minor product. And then the difference between the second and third resonance structures is that there's just a different placement of the double bond and a positive charge. So both of these are going to be the same as far as ability goes. And so these will both be our major products. Okay. I apologize for the screaming kids in the background. All right, let's draw our hybrid structure. Again, we always start with our base structure with no double bonds, no lone pairs, okay, just our base carbon, oxygen, and our assumed hydrogens, okay? Now, we'll start with lone pairs. Oxygen, the lowest number of lone pairs oxygen held in any of these was just one set of lone pairs, so we're going to draw that, okay? At one point, we have a double bond right here. So we can do a dashed line. At one point, we have a double bond right here. So we'll do a dashed line and the same for right here. Do I need to do a dashed line right here?
No.
No, right? Because there was never a double bond right there. Okay. All right. Now we need to look at placement of our positive charge. So at one point, oxygen held the positive charge, so there's a partial positive there. At one point, this carbon had a positive charge, so there's a partial positive. And at one point, this carbon had a positive charge, so it has a partial positive. And that is our hybrid. Any questions on that one?
Nope.
How are we doing? Is what I'm explaining everyone understanding? Let's see, where does the second lone pair go? That's what is in the double bonds. So right here in our original, we have two double bonds, whereas in both of these resonance structures, there's only one. And so that's where like the second set of lone pairs goes. So it comes from the double bond, and then we only end up with one double bond. Okay. How's my explaining going? Is everyone understanding okay?
Perfectly.
Yeah.
Okay,
If
perfect.
it was a triple bond, would it still be a dashed line?
If there was a triple bond, did you say?
Yeah.
Yeah, so if there was ever a triple bond, all you have to do again is draw your base. So let's say if we had something like this, right? We wanted to, I don't know, how would that look? Let's say, for example, I'm not going to draw the whole thing, but if we had something like this, right? Where at one point there's a triple bond here, and at one point there's a double bond. All we do is say the least number of bonds there ever was a double bond, and then the third one is a dashed. Does that explanation make sense?
Yeah. Thank you.
You always talk about the base number, the lowest number there ever was in any of the structures, and then if there was more, then you add those on.
Okay. Cool. Thanks.
Yep. All right, let's carry on. Okay, we got a couple more resonance structures here. What's unhappy and how can we fix it? We have a negative charge on our carbon. And so we don't want to move electrons towards carbon, so let's move electrons away. All right, so this set of lone pairs, let's go ahead and move it and create a double bond. And then doing so would break the octet for the left side carbon. So we need to break this double bond and move it onto oxygen. Okay. So we're going to have C double bond C, hydrogen, 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 and then an oxygen, which now has 3 sets of lone pairs and a negative charge. Okay. All right. Now there's nothing else we can do to this structure to change it again, right? So let's determine major and minor. Which one is more stable, do you guys think, left or right?
The right one.
The right one, right? Okay, because oxygen is better at holding negative charges than carbon. So this will be our major and our minor. So now we need to draw our hybrid. We've got carbon, hydrogens, oxygen. Okay. Do we need to put a lone pair right here?
No.
No, right? Because at one point we have carbon that does not have any lone pairs. Okay, so no lone pair there. Least number of lone pairs on oxygen?
2 set of lone pairs.
2 sets of lone pairs. Is our least number. Okay. We'll do our double bond, partial double bond there, partial double bond there. We have a partial negative, partial negative. Okay. Any questions on that one? Okay. Number 4. What's unhappy and how can we fix it? Carbon at the bottom that has a positive charge. So we don't want to move electrons away from that carbon because it's already positive. So we want to move electrons towards it. We do have a double bond here that can help out. So let's move the double bond down like that. Okay. All right, so now we have a double bond here. The oxygen remains how it was. And we have a positive charge right here because there was electrons there with the double bond and now they're gone, so it becomes more positive. Okay. All right. Now again, we have a carbon that's unhappy. Is there anything we can do besides undoing what we just did to make it happy? The answer is yes. We can move lone pairs from oxygen down here and form a double bond. And then we would get double bond here, double bond here. One set of lone pairs now. And a positive charge on that oxygen because it wants 6 and it now has 5. Okay. Any questions on that one so far?
Mm-mm. Looking good.
Okay. Let's talk major minor. Okay. We have a positive charge on an oxygen and then positive charges on 2 different carbons. So we know carbon is more happy holding negative charge. So this is going to be our major. Sorry, this is going to be our minor. Because oxygen doesn't like positive. And then here we have a carbon that's holding it, and here we have a carbon that's holding it. So these are both going to be major. Let's talk hybrid structure. Okay, we'll do lone pairs first. At one point, oxygen only has 1 set of lone pairs. We're going to do 1 set. Talk double bonds. So at one point, we have a double bond here, here, and here. Any others? No, it doesn't look like it. All right, now we need to do our charges. So at one point we have a positive charge on the oxygen, this carbon, and this carbon. That's our hybrid. Any questions on that one?
Nope.
Cool. Let's carry on. All right, so now we're going to talk geometry, hybridization, bond angles of the following molecules, okay? And I've got some tricks here to help you guys remember these. So let's first talk about CH4. As far as geometry goes, what do you guys think? Is it going to be trigonal pyramidal, trigonal planar, tetrahedral, bent? What do you guys think?
Tetrahedral.
Tetrahedral, right? We've got a central atom with 4 things around it, so it's going to be tetrahedral. What's the hybridization, sp2 or sp3?
sp3.
Perfect. All right, we know that because the carbon has 4 regions of electron density around it, and we always do the number of regions of electron density minus 1, so sp3. All right, and anyone remember the bond angles for tetrahedral molecules?
I think it's 109.5.
109.5 degrees. Okay. And if you can remember this one, you can remember all of the other ones. And I'll talk to you about why in just a minute. Okay. If you can remember that tetrahedral is 109.5, there's a way to remember the rest of them. All right, let's talk about this nitrogen. It's got 4 regions of electron density, so it's going to be sp3 still. But what about the geometry?
Pyramidal.
Yeah, trigonal pyramidal, right? When something is sp3, but it has 1 region of electron density, or sorry, when it has 1 set of lone pairs, that's going to make it trigonal pyramidal. Okay, and the bond angle here is 107 degrees. Okay, now how to remember this one based off of our tetrahedral, right? If you have 1 set of lone pairs, how many electrons in a lone pair? 2. So we have 2 electrons around the nitrogen. 109 minus 2 gives you 107. Okay. So you got 2 electrons around that nitrogen that are not bonded to anything. 109 minus 2 is 107. Okay, a little trick there. Let's go down and do this one now because we'll talk about our trick here again. Okay. First of all, what is our geometry for this?
Trigonal planar.
Okay, not quite.
Oh,
We
wait,
got-
sorry. Which one?
Planar.
Okay, not planar. When there's
Which one are we looking at?
four
actually?
regions of electron. Sorry, what was that?
Which one are we looking at? The carbon chain and the oxygen?
Right here. Yep.
Oh, okay. Tetrahedral.
Oh,
Not quite, because tetrahedral is when all of the electrons are bonded. Okay. So we've got 2 bonds and 2 sets of lone pairs. What does this kind of remind you of? It kind of looks like
Ben.
a water molecule, right? Perfect. Bent. Okay. This one is bent. Okay. A lot of people remember the water molecule is bent. That kind of looks like a water molecule, right? So when you've got 4 regions of electron density, or sp3, and there's 2 sets of lone pairs, that's going to be bent. Okay. Now again, remembering the bond angle here, we've got 4 unbonded electrons. 109 minus 4 gives us 105 degrees. Okay. Is that kind of helping you guys remember the bond angles here? Does that trick help?
Definitely.
Perfect. All right, so 105 there for the bent molecule. All right, so let's hop back up here to this ketone. Okay. So we're talking about this carbon right here. What's the geometry around that carbon? 3 regions of electron density, no lone pairs,
Trigonal planar.
trigonal planar, okay. We know that because there's 3 regions of electron density, right? Okay. And so reminds you of trigonal, right? 3, trigonal, tri. And then planar because it's all in one plane. If there was lone pairs, that would force the other bonds to kind of separate a little bit more and then they go into different planes. But this molecule is completely flat. Okay. So that's what makes it planar. There's one plane. All right. We said 3 regions of electron density makes it sp2 or sp3?
sp2.
sp2. All right. And then bond angles on here, we're going to do 360 divided by 3 gives us 120. Because there's 3 equidistant angles here, and the total would be 360. So that gives us 360 divided by 3 is 120. All right, how about for this molecule right here? Geometry.
Linear.
Linear, okay? Any triple bond is always going to be linear. Okay? All right, 2 regions of electron density. Is it going to be sp, sp2, or sp3?
Just sp.
sp, okay? Because there's only 1 region with the triple bonds, and second region is with the C bond H. 2 regions, 2 minus 1 is 1 sp. All right, how about bond angles here?
180.
180, okay. 180 degrees because 360 divided by 2 is 180. Awesome. Now let's talk about this nitrogen right here. First of all, is there a set of lone pairs on that nitrogen or no?
Yes.
Yes. Nitrogen wants 5 electrons and only shows the 3 that it has in the bonds. So we need to add a lone pair. Okay. So 3 bonds and 1 lone pair, what does that give us?
Pyramidal.
Yep. Trigonal, pyramidal. Okay. SP, SP2, or SP3?
SP3.
sp3 because of the 4 regions of electron density. Okay. All right, again, we've got 4 regions of electron density with 1 set of lone pairs. So what's our bond angle going to be? Use my trick here.
And 7.
107. Okay, again, if it's just tetrahedral, it's 109.5. Okay, and then if there's 1 set of lone pairs, it pushes it down by 2, giving us 107. Perfect. Any questions on those before we move on? The names as far as, trigonal pyramidal, trigonal planar, bent, linear, you just got to memorize those, get used to those. You can find lots of online practice. Just look up OChem geometry practice. You'll get lots of results. All right. Rank from smallest to longest bond length and from weakest to strongest. So what's going to be our smallest bond length? A single, double, or triple bond?
Triple bond.
Triple bond, right? So let's say this is molecule A, B, and C. So our triple bond is going to be the shortest bond length. Okay. How about the next one? What's going to be the middle length? Our double bond, right?
Mm-hmm.
And then our single bond is going to be the longest. Cool. And then we've got from weakest to strongest. What's our weakest bond? A double, single, or a triple?
Weakest is
The single bond is the weakest.
Perfect. Single bond, right? So A is our weakest bond. Okay. Then our double bond next. And then triple bond is the strongest. So this is from shortest to longest. This is from weakest to strongest. Beautiful. Any questions on that? You just kind of got to remember that trend. He loves questions like this, ranking questions. Rank from longest to shortest, weakest to strongest, most acidic to least acidic, most basic to least basic. Okay, these are all questions you're going to have on your exam, especially because there's a lot of multiple choice. It's all multiple choice. Okay, so you're going to have to get really used to being able to put these in a certain order. Okay. All right, so we're going to write the sigma and pi bond properties for the C double bond O and write the hybridization geometry and bond angle. So we're talking about this bond between the carbon and oxygen. Okay. So first of all, what's the sigma bond here? What do we need to look at? We have C bonded to oxygen. What hybridization is the carbon? SP, SP2, SP3.
SP2.
SP2. Because this carbon has 3 regions of electron density around it. 3 minus 1 is 2. How about the oxygen?
SP2.
It's SP2 as well, right? It's got 2 sets of lone pairs and then a double bond that gives it 3 regions of electron density, making it SP2 hybridized. Okay. So we also want to talk about the pi bond. Okay, pi bonds are super easy. You just got to memorize this, okay? Pi bonds are always going to be C2P O2P. Okay. If it was a carbon double bond carbon, it would be carbon 2P, carbon 2P. Okay. So you just got to remember 2P for all of your pi bonds. All right. So now we've got the hybridization. What about the geometry around that carbon? What do you guys think?
Trigonal
It is trigonal planar. We've got 3 regions of electron density, no lone pairs, so it's all in one plane, trigonal planar. And bond angle for trigonal planar is 120. Perfect. Any questions on that one?
I do have a question for like pi bond. If there was like triple bond to it, then there will be two pi bonds, right? Then
Yep.
how do you write the hybridization for that?
Yeah, let's do it for this molecule. Okay, is that all right?
Yeah.
So our sigma bond would be carbon sp, carbon sp, okay, because they both have 2 regions of electron density. Then we'd write pi 1, okay, and again it would be C2p, C2p, and pi number 2 would be C2p, C2p.
Oh,
So for triple bonds, it's just the same. You have to separate them as pi 1 and pi 2. That's the only difference. Perfect. All right, label the following as polar and non-polar. Okay. So what you're going to want to look at here is if there is an atom which is electronegative, pulling electron density towards it. For this one, we have an oxygen which is pulling electron density this way. Is there anything which is pulling the opposite direction to cancel out that pull?
no.
No, right? So this one is polar. Okay. Again, with this one, we've got oxygen pulling this way, oxygen pulling this way. Okay. Because those are in exactly opposite directions, they cancel each other out, making this one non-polar. Okay. Now CH2Cl2. First of all, let's draw that out. So we have 1 carbon bonded to 2 chlorines and 2 hydrogens. Doesn't matter where you put those around the molecule, just so long as you've got your 2 hydrogens and 2 chlorines. Okay. All right, so now this is a tricky one. Okay, let's talk about the geometry of this one. What's the geometry here? Tetrahedral, right? Okay. So what do we know about the bond angles on tetrahedral?
109.
9.5, okay. Most people will look at this molecule and they'll draw it like this. And they'll say, well, chlorine's pulling that way and chlorine's pulling that way. They cancel each other out, non-polar. But we know the true structure of this molecule is tetrahedral, right? And all of the different bonds around the central carbon are 109 degrees apart from each other. Okay, they're not 90 degrees or 180 from each other in the chlorine sense. Okay, so we know, even though sometimes we might draw it like this, because they are not exactly opposite from each other, the chlorines are pulling in different directions, which makes the overall molecule polar. Okay, does my explanation make sense there? Don't fall for the trap of drawing the molecule like this. Okay. If you're confused, make sure you draw it out and determine what the bond angles would be. If it's 180, like in, a linear, okay, then they can cancel each other out, but otherwise they will not cancel each other out. Does that make sense to everybody?
Mm-hmm. Yes.
Excellent. Moving along here, which of the following has a larger dipole moment? Okay, so what we're looking at here is to determine which one pulls stronger on the, pulls electron density stronger, okay? So this oxygen is pulling electron density this way, same as this oxygen. Which one do you think is going to be a larger dipole moment? Left or right?
Left.
Right.
Left, right? Because these chlorines are pulling electron density opposite, not exactly opposite, but in a different direction from the oxygen that's pulling up. Okay, so this oxygen isn't having to compete with any other electronegativity, so it's going to have a larger dipole moment. All right, how about between these next two, sulfur and oxygen? Okay, we got the same molecule other than the atom that's bonded there. Which one's going to have a larger dipole moment?
The oxygen one,
Yeah, why?
because it has the higher electronegativity.
Perfect. Oxygen is more electronegative than sulfur, so it's going to pull electron density stronger than sulfur. Awesome. All right, so now we're moving on to chapter 2. So we want to draw the arrow pushing conjugate acid and base and which way the reaction will prefer. So first of all, let's label our acid and base here. Okay. Which one's our acid?
The first one, the HC3.
Okay. What does an acid do? Let's talk about that first.
It accepts protons.
Yeah, it accepts protons. Or sorry, an acid donates protons.
Oh, right? Yeah, my bad.
Okay. Sorry, I had it backwards too. Okay. Acids donate protons. So if this atom was to donate a proton, what would it become? Sorry, it doesn't go like that. Something steals the proton and then the electrons go up onto there. It would become 2-, right? It would have extra electrons, way more electrons than it wants, okay? So this is actually going to be our base, okay? A way to know if something is a base, commonly they'll have a negative charge on them, okay? Or there'll be a partial negative, meaning that something is, pulling electron density in a certain way, and so it's going to be more, more negative, if that makes sense, okay? So look for a negative charge. That'll tell you it's a base for sure. Okay, so that's going to be our base. This is our acid. This also, we know this is an acid because it has a proton to give, okay? Oxygen is okay holding a negative charge if that proton was to be taken. Okay? So we know that this is going to be a better acid because it's better at holding that negative charge. Okay? So in acid-base chemistry, our base always steals a proton from the acid. Okay? So the base is going to reach out and steal this proton, and then the electrons in this bond are going to go onto the oxygen. Okay. So I'm just going to draw an arrow like this for now. Okay, and then we'll talk about which way it's going to prefer in just a minute. Okay, so now we have CH4, right, with no charge. Okay, and we also have an oxygen, which is negatively charged like that. All right, which one's our conjugate acid and our conjugate base? Which one's our conjugate acid?
CH4.
CH4, perfect. And our conjugate base is here, which is the negative charged oxygen. All right. Let's see, did I arrow pushing conjugate acid and base and which way the reaction prefer? Okay, so if I was to tell you that the pKa of this acid is 3.7 and the pKa of this conjugate acid is 28. Which way is this reaction going to prefer? towards the products or towards the reactants?
Towards the reactants.
You're saying going this way?
Sorry, my bad. Products.
Okay. Why do you say products?
Because the left side has a lower pKa, which means it's a stronger acid, which means it'll
Prefer going towards the products, right?
I don't know how to say it, but
Yeah, so what you want to look for, the lower the pKa means a stronger acid. And a stronger acid is going to dissociate easier, or it's going to give up its proton easier. Okay, so that means it's going to prefer going towards our products versus our reactants because this acid is a stronger acid than this one. Does that make sense to everybody? The pKa, because it's lower, means that our products will be preferred, okay, because this is a stronger acid. So always your preferred direction is going to go away from the stronger acid, and our lower the pKa is, the stronger acid. I hope that makes sense. We okay?
mm-hmm.
Okay. All right, let's label our acid and base. Again, I told you negative charge, that's going to be a base. So this will be our acid. Okay. Acid-base chemistry, our base is going to steal a proton. Okay. So this is going to reach out, steal a hydrogen. Those electrons will go onto that carbon, giving us this product. We're going to have this as well. And feel free to draw the lone pairs on here if you want to as well. They're not required, but you can. All right, which ones are conjugate acid?
The right one.
Yep.
Joe, H3.
Conjugate acid, conjugate base. Now, if I was to tell you the pKa of this acid is 7.2, and the pKa of this acid is 47. Okay, these are not realistic numbers. I'm just making them up. But which way is our reaction going to prefer?
Products.
Products, right? So we're going to have a bigger arrow going towards our products, away from our stronger acid.
I have a quick question.
Yep.
So what kind of helps me sometimes, because I determine it based on the structure of the, looking at the base, the conjugate base.
Yep.
And I look at which one's more stable, right? Like that's how we determine acid strength sometimes.
For sure, yeah.
So for me, I think as a shortcut, like, okay, well, what's the most stable one? And will the reaction prefer the more stable base, I guess? So would that work?
Yep, that would for sure work, right? This base is more stable than this base, right?
Yeah.
Because this negative charge can resonate. Those electrons can form a double bond here, and then the electrons can go up onto there, whereas this base cannot resonate. Okay, so that makes this one more stable. And so our reaction will prefer the more stable base. It's a good way of looking at it too. That's actually what's happening, but you know, he'll usually ask you based on the pKa's.
Mm-hmm.
Okay. That's why, you know, that's why this pKa is lower. That's why this one's a stronger acid, because when it loses that proton, it becomes more stable. Okay. All right. Again, we've got our base and our acid. What is our base going to do?
Base is going to accept the proton.
Yeah. It's going to steal this proton, right? Or accept the proton. And these electrons will go onto the carbon.
Yoink.
Okay, and then we also have NH3. You could draw out the structure with the 3 hydrogens as well if you wanted to. All right. Which one's our conjugate base?
He left the HC2.
Yep. So we got conjugate base, conjugate acid. All right. If I was to tell you that the pKa here is 31 and the pKa is 12, which way is our reaction going to prefer, products or reactants?
The reactants.
Reactants, right? It's going to go away from the stronger acid. It's going to prefer the left side. All right, any questions on acid-base stuff? Shouldn't be anything too crazy. Just determine which one's your acid and base. The base is going to steal a proton and should be good to go. Make sure all of your charges are set. All right, carrying on. Which hydrogen in the following molecule is the most acidic? So how we're going to determine these is if you want to look at it kind of like who was saying that they look at which base is more stable in the last problems, right? So we're going to want to look at if the proton was to leave, right, then which one is going to be the most stable. So let's call this HA, these hydrogens here, HB, HC. Which one do you guys think is the most acidic proton?
C.
Which one did you say?
C.
C? Why C?
I thought the oxygen, the hydrogen and the oxygen will be like.
Yeah, right. If that
easier.
oxygen, what's that?
No, you can carry.
Yeah, so if that oxygen was to lose that proton, right, it's going to have a negative charge, okay? So oxygen is pretty stable holding a negative charge, whereas if this hydrogen was to leave, right, then the carbon would hold a negative charge, which isn't as stable as oxygen. And if nitrogen was to lose a proton, the nitrogen will hold a negative charge, and it's not as stable as oxygen. So that makes HC our strongest acid, or most acidic. Okay, let's call this one HA, HB, HC. Okay. Which one is going to be our strongest acid, most acidic proton?
HB.
HB. Okay. So let's compare A and C. Okay. First of all, if A was to get taken, okay, this carbon would hold a negative charge. Okay, and that can resonate. Okay. So that's pretty stable, right? If something can resonate.
Mm-hmm.
Whereas if nitrogen was to get the negative charge, that can also resonate. So nitrogen is going to be more stable than carbon. So we know it's going to be either B or C, okay? But if we were to lose HB, this nitrogen would have a negative charge, so as stable as C, but it can resonate both ways. It has two options to resonate, and so it makes HB a better acidic proton, okay, because there's two options to resonate. Okay, so HB is going to be our strongest acid. Does that make sense to everybody?
Yes.
Excellent. Questions before I move on? Okay, So we're going to want to rank these acids from weakest to strongest. Again, like I said, he likes ranking questions, so get used to these. All right. So what we're going to want to look at is the stability of the conjugate base. Okay. So if NH3 was to lose a proton, it would be NH2 minus, right? Same as CH3 minus and OH minus. Which one is the weakest of those three? Which one is the least stable?
CH4 or the
CH3 negative, right? So that means that CH4 is going to be our weakest acid. Okay, which one's next? NH3, right? Okay. Because OH minus, oxygen is okay holding that negative charge over nitrogen and carbon. Okay.
mm-hmm.
So that's going to be our ranking like that. All right, give this second one a try. I need to go grab some water. I've been talking too much. Give me just a second. All right, I apologize for that. Okay, so what do we think on this one? What order did you guys put these in?
Put CH4 is the weakest, and then C2H4, and then C2H2 is the strongest.
C2H4, C2, my goodness, I keep doing that. C2H2. Okay, so let's look at the structures here and make sure we got that right, okay? C2H2 is going to be a triple bond, right? C2H4 is going to be a double bond. Okay, and then CH4 is obviously something like that, right? Okay. So the strongest one, right, we've talked about this in the past, is going to be the carbon triple bond, okay? Because if it was to lose the proton, that triple bond is very strong. It's stable, right? And so that's going to be the most stable. So we got that exactly right. The triple bond is going to be most stable, then our double, then our single bonds. Perfect. Let's talk about number 3. Okay. So if we had this proton leave, okay, then we'd have a negative charge here, which can resonate. Okay. Here we just have a negative oxygen with no way to resonate. And here we'd have an ability to resonate with the nitrogen. Okay. So what's going to be our weakest? A, B, or C?
B.
We got B, then what's next?
C.
Perfect. A, right? Beautiful. Any questions on those? All right, is HF or HI a stronger acid? What do you guys think?
HI.
Why is that?
Because it's has a bigger size, so we can hold that charge better.
Perfect. Yeah, you got that exactly right. Okay. So although hydrofluoric acid, the fluorine is more electronegative than the iodine, fluorine, once it actually gets that negative charge, it's so small that it has a hard time holding those electrons, okay? So although it pulls the electron density more, fluorine is not able to hold the charge as well as iodine, because iodine is huge compared to fluorine, right? So HI is going to be our stronger acid because when it actually holds that negative charge as a base, it's going to be more stable. Okay, so let me ask the question then, which would be a better base, fluoride ion or iodine ion? F minus or I minus, stronger base. Okay, we got an I minus. Which one of these is more stable? Okay. Iodine is going to be more stable because, yep, perfect. Thanks, Tanner. Iodine is more stable because it's bigger and holds a negative charge better. So fluorine is going to be a stronger base, okay, because it's less stable, and so it's going to try to find any hydrogen anywhere to try to steal and become hydrofluoric acid. Okay, so it's a stronger base, fluoride ion. Okay. Let's talk functional groups. Start naming some that you guys see in these molecules, in this first molecule. Anyone, just shout them out. Any that you see.
Carboxyl acid. Carboxyl acid.
Carboxylic acid, perfect. What's next?
Ketone. The double
Sorry?
bond water. The ketone.
Ketone? So you're talking about this one right here, right?
Yeah.
Okay, so that one is actually part of a larger group. Does anyone know what the larger group is? Ester, perfect. So because the ketone has an oxygen instead of, a ketone is when there's a carbon on either side of the C double bond O, right? But because one of them was an oxygen, that made an ester. Okay, and I like to remember that one like there's lots of oxygens. Okay, there's two oxygens which look like Easter eggs. Ester kind of looks like Easter eggs. I don't know if that helps, but helps me. So, okay, we got aromatic. I saw someone in the chat.
Alcohol on the end.
Sorry, what was that?
Alcohol.
Yes, we have an alcohol. What degree alcohol is that? 1 degree. Okay, that's because we look at this carbon right here and we determine how many carbons are bonded to that carbon, and there's only one. Okay, so that makes it a 1 degree alcohol. All right, there's one more functional group that he could test you on.
It was something like THI, something.
Thiol?
Yeah.
Okay, close. That's if there's an SH, okay? Close, okay? So you know you're in the right ballpark, okay? If it's just sulfur by itself, it's sulfide. If it was like an SH on the end of a group like that, because it has a hydrogen, that would be a thiol. Okay, but very close. All right, let's talk about the second molecule. Just shout them out. Let's hear them.
Alcohol.
Alcohol. What degree alcohol is it?
First.
No, not quite. So we want to look at this carbon. Okay, how many carbons are bonded to that carbon?
Okay. The other ones. The 3.
2. Okay, we got 1, 2.
Oh, okay.
Okay. but very close. Okay, so that's how you determine it. It's kind of funny how they do that. It's like the OH is the alcohol, but then to determine how many degrees it is, you look at the carbon bonded to the alcohol and how many carbons are bonded to that carbon, right? It's kind of confusing, but if you understand that the full functional group is the carbon bonded to the OH, then you can kind of start to see, okay, how many carbons are bonded to our functional group? 2, okay? 2-degree alcohol. Let's see, in the chat we had aromatic, perfect. And we had an amine, perfect. Okay. What makes this one an amine and not a amide?
Oxygen.
Yeah, because there's a C double bond O there, right? Okay. So that's what we want to look for, right, with this molecule is because there's a nitrogen that's bonded to a carbon that's then double bonded to an oxygen, this whole thing is called an amine. Okay. Or sorry, not an amine, it's an amide. I'm sorry. Amine is if there was no oxygen, okay? And we'll talk about the difference here in just a minute, okay? So it's an amide, okay? And then in fact, let's go to that right now to determine the difference, okay? Right here we have an amine. There's no double bond to oxygen, right? So how I remember the difference, so amine and amide are very similar words, but an amide, okay, amides hide, amide hide. Amides hide behind this C double bond O, okay? This amide hides behind the C double bond O, whereas on this one, this amine is mean to oxygen, and so there's no oxygen around it, okay? Amines are mean. Amine, mean. Amide, hide. Okay, does that kind of help you guys remember the difference? Amide, hide, amine is mean. There's no oxygen close by. All right. I apologize for the confusion there. Any questions on the difference there?
Mm-mm.
All right. Then we've got any others you guys see in here?
Ether.
Ether, perfect. Right here is an ether. Okay, and ether and ester are a lot alike. A lot of people get those confused, right? So over here we had an ester, which is an oxygen with 2 carbons on either side, but then there's also a C double bond O. Ester is like Easter because there's 2 eggs, okay, 2 oxygens, whereas ether, if you guys know, the general way to write carbon groups is an R, right? If in organic chemistry, if someone says there's an R group, that means you know that there's some kind of carbon chain, okay? And so the way to write an ether is to say ROR, so either or, OR, either or. I don't know if that helps, but that's a way to remember it if you're having a hard time. It kind of looks like OR, right? OR group. Okay. And I see one more in this right here. What do you guys think? See any others? We haven't talked a lot about it yet, so you may not recognize it. C double bond Cs are called alkenes. I don't think he's going to test you on this exam, but I wanted to bring it up just in case. Okay. If it's a C single bond, carbon like that, is called alkane. C double bond, alkene. C triple bond, alkyne. And those kind of go in alphabetical order. Alkane, 1. Alkene is double bond, and alkyne is triple bond. I don't think he's going to test you on it for this exam, but just be aware of those just in case he brings it up. All right. Any questions on those so far?
Nope.
Awesome. Let's talk this one. What do you guys see?
Carboxylic acid.
Perfect. What else?
Aromatic.
Aromatic. What's this right here?
Amine.
I think I heard it. Amine. Is that what you guys said? Amine, right? Okay. That one's mean. There's no oxygen around. Okay. He's mean. Any others we see?
There's another. Oh, never mind. I was say there's another carboxylic acid at the end, but
Okay, we talked about this one a bit earlier. What's this? If there's no OH on there, what does it become? Anyone remember? Aldehyde, perfect. Good job, Tanner. Cool. All right, and then the last one is this right here. What's this one? Yes, perfect. 3-degree amide. Let's see, actually, I think it's a 2-degree amide because we want to look at the carbons that are bonded to the nitrogen. Does anyone know for sure? Can't remember the exact rules in a while. But I would say 2-degree. Very good, though. What degree amine is this?
First degree.
First degree, right? Primary amine. All right, that's functional groups, okay? Get familiar with those. Again, there's good practice online. If you Google organic chemistry functional groups, there will be some on there that he won't expect you to know yet, but it should be some good practice. All right, let's talk about boiling point. Rank from highest to lowest boiling point. Okay, so what determines boiling point?
Intermolecular forces.
Perfect. So let's write, what are the intermolecular forces on A?
Van der Waal.
Okay. Every molecule is going to have van der Waal forces. Okay. Van der Waal, is there any others?
Okay. So.
None others for A. How about B? Again, we got van der Waals, always van der Waals. What else?
Dipole.
Dipole, yep, we saw that in the chat as well, dipole. And then, is there any others?
That's it.
Okay, we have one more. Hydrogen bond. Okay. Remember, hydrogen bond can happen with fluorine, oxygen, nitrogen. Okay. And I like to remember that. My wife owns a business called Desert Fawn. F-O-N, fawn. Okay. Fluorine, oxygen, and nitrogen.
I thought that was only if the hydrogen is bonded to one of those.
Nope. So what would happen is this nitrogen would hydrogen bond with hydrogen in one of the other molecules like that. So like if this next molecule over here had a CH3, they'd hydrogen bond together, that nitrogen and those hydrogens.
Oh.
So they can hydrogen bond even if there's no hydrogen directly attached.
Oh, okay.
Okay. All right. So let's talk about C. Again, we have van der Waals. We have dipole-dipole. And is there hydrogen bonding here?
Yes.
Yes. Right. H bond. All right. So we know our weakest is going to be A. So we can put that because we want it highest to lowest. So we're going to have A on that right side. Okay. Now it's a little tricky. Okay. But he might test you on this. The difference between B and C is how exposed the nitrogen is in order to hydrogen bond. Which one is easier to get to? Which one is more exposed to the outside? C, right? So it's C has a better time hydrogen bonding with other molecules than B. That would make C higher boiling point than B. Does that make sense to everybody? Because this is a 1 degree amine, and this is a 3 degree amine. Okay, so the 1 degree is more exposed, more able to hydrogen bond. Okay. All right, let's do number 2. We got van der Waals forces. Anything else for the first one?
That's it.
Okay. How about for B?
It goes van der Waal, dipole, and the hydrogen.
Van der Waal, dipole, H bond. Okay. Same for C, right?
Mm-hmm.
Okay. What's the difference between B and C?
It has the nitrogen and an oxygen on C.
Yeah, perfect. There's one area of hydrogen bond, one chance for hydrogen bonds. Whereas over here we have 1, 2, 3 areas for hydrogen bonds. So C is going to be our highest boiling point, then B, then A. Any questions on those? Like I said, he likes ranking questions. All right. So we want to determine if the following molecules will be water soluble. Okay. So the rule here is you want to look at the number of electronegative elements versus the number of carbons. And the rule is a 5-to-1 ratio. Okay. For every one electronegative element, you can have up to 5 carbons. Okay. If it goes to a ratio of 1 to 6, this molecule will not be water soluble. Okay. So let's talk about this first one in the top left. All right. How many electronegative atoms?
2.
2, right? 2 oxygens. So we can have up to 10 total carbons in this molecule for it to still be water soluble. So let's count the number of carbons. How many carbons in this molecule?
7.
7, right? So we have a 2-to-7 ratio, which means we're good. It is water soluble. Does that make sense, the process on these?
Yes.
Perfect. All right, let's talk about the second one. We have 2 electronegative elements. So we can have up to 10 carbons. How many carbons?
5.
5, right? So that checks out. They are water soluble. This molecule is water soluble. Okay. Talk about this one right here. Two to 10, right?
Mm-hmm.
How many carbons in this molecule?
11, I think.
11, right? So we have broken our rule, which means it is not water soluble. For you biology buffs out there, what molecule is that? What is that molecule? You know? It's a lipid.
Dang.
It's what creates our lipid bilayer around our cells. One of them. One of our lipids. All right. So we have our water-loving side. Okay, that's on the outside of the cell. And this is the inner part of our lipid bilayer, fatty acid tail. Just a little trivia there. All right. So in this molecule, we have 4 electronegative atoms. So we can have up to how many carbons? 20, right? Perfect. How many carbons in the molecule?
13.
13. So we have 4 to 13. Checks out. It is water soluble. All right. IUPAC naming. We're almost there, guys. Almost there. I know it's been a long day. Using IUPAC naming rules, name the following molecules. Okay. So first we want to determine how many are in our longest chain and which direction we want to number. Okay. So first of all, what's our longest chain? How many carbons?
6.
6, right? And are we going to number left to right or right to left? What do you think?
Right to left.
Right to left. So we have carbon 1, 2, 3, 4, 5, 6. Why did we number right to left instead of left to right?
Because the first, I don't know what it's called, but the first branch, I guess, is the one to the right, which is 2.
Perfect. So we want our substituents, is the word you were looking for, at our lowest numbers possible. So here we have substituents at 2 and 4. If we were to number it the other way, they'd be at 3 and 5. Okay. So we want to number this way because they're at lower numbers. Okay. So we have 2 what substituents? What are these substituents called? They're methyls, right? Perfect. Good job, Tanner. So we have 2,4-dimethyl. Okay, then we want to name the parent chain. What is our parent chain? 6 carbons.
Hexane.
Hexane. 2,4-dimethyl hexane. Any questions on that one? All right. We want to determine our longest parent chain. How many in our longest chain?
9.
Perfect. 9 in our longest chain. And I numbered this way because we have a substituents at a lower number. Okay. Then the way I like to do this is I like to write out my substituents that I've got before I even start trying to name it. So I've got a 3-methyl. And then what is the group at 6 called?
Isopropyl.
Isopropyl. Nice job. Isopropyl. Perfect. So we're determining alphabetically which comes first between M for methyl, and I for iso. Okay. So isopropyl comes first alphabetically. So the name of this is going to be 6-isopropyl, 3-methyl, and what's our parent chain?
Nonane.
Nonane. Perfect. Nice job. Okay. 6-isopropyl, 3-methyl nonane. All right, let's talk about this next one. I'm going to start at the bottom here numbering because I know that this is going to give us our lowest substituent numbers. 1, 2, 3, 4, 5, 6, 7. And then is it better to go down or better to go across? What do you guys think?
I think across.
I actually remembered there was a mistake on this one. Let's ignore this last carbon and say that this is our final carbon. Okay. So this will be 8, 9, 10. Because he doesn't expect you to know any more than the first 10. Okay. All right. So we've got, what are our substituents?
3, 4, 7, 8.
3, 4, what? 3, 4 dimethyl.
7 is isopropyl.
7 isopropyl. 8 what? What's that group? Tert-butyl. Perfect. Okay. Nice job. I remember tert-butyl because it kind of looks like a turkey foot. Okay. Turkey, tert-butyl. All right. Alphabetically, which one are we going to determine between? Are we using the T for tert or B for butyl?
B.
Perfect. Okay, there's only 2 in which we use the B for butyl, okay? And that's sec-butyl and tert-butyl. Okay. And how you remember that is that these 2, they have dashes in them. All of the rest of them, like, yeah, so we had a question, do I use I for iso? Yes, because there's no dash. So sec-butyl and tert-butyl have a dash, and so that's why you use the B, whereas for, isobutyl, isopropyl, all of those different groups, they don't have a dash, and so you're going to use the I for iso, right? So the only ones that are going to use anything other than the first letter is sec and tert-butyl. Okay, and you can remember those. If you remember the spelling of those 2 that they have dashes, then you'll know that's how you choose them alphabetically. And I promise you, he will test you on that one. So make sure you know it. Okay, so what comes first alphabetically?
Butyl, tert-butyl.
Yep, so we got an 8 tert-butyl. Then what?
Isopropyl.
7 isopropyl. 3, 4 dimethyl. Then what's the parent chain?
Decane.
Decane. Perfect. And I did put at the top here just some kind of ways to remember, kind of the order they go in. So you can remember the IUPAC naming rules there. But just remember that substituents, you're always going to end them in YL, right? Isopropyl, butyl, methyl. But if that was the parent chain, if there was a 4-carbon parent chain, it would be butane. Okay, that's where we're getting those. This tert-butyl has 4 carbons, which is butane, but because it's a substituent, we call it butyl. Does that make sense to everybody? Just a little reminder there for naming. That's why we call, like, methyl is only 1 carbon, but if there was only a 1 carbon chain, it would be methane, right? CH4, methane. Okay. A few little reminders there. Okay. So we want to look at our substituents. For rings, you want to determine if there's a carbon chain longer outside of the ring or if the ring is the longest carbon chain, okay? So we can see here we have 1, 2, 3, 4 carbons in this chain, whereas we have 1, 2, 3, 4, 5, 6 carbons in the ring, okay? So our ring is going to be the parent chain here, okay? So now we need to determine between numbering how we're going to number this, right? So here we have what? What functional group is this?
Propane.
Okay, it's got 4 carbons. Propane is for 3.
So butane.
Yeah, butane, right? So we have a butane and we have a methane. And because they're substituents, we can call this a butyl and a methyl. Okay, alphabetically, which one comes first? Butyl, right?
Mm-hmm.
So that's how we determine how to number our ring. So then our number 1 substituent, our alphabetically first substituent is our number 1, and then we number clockwise or counterclockwise depending upon which one will give us our lowest number of substituents. This time it doesn't matter because it's directly opposite, so we can number it this way or we could number it this way. You see how 4 still lands on the same one? Okay. So this is going to be, we can name it like that or number it like that. Okay. So we have a butyl, okay, 4-methyl. Then what's our parent chain?
Cyclohexane.
Cyclohexane. You can call it 1-butyl if you want to, but it's not necessary. Okay.
Question real quick. So would we technically get it wrong if we started with 4-butyl and then 1-methyl?
Yes, because you want to put it because of alphabetical order. That's right.
No, but I'm talking about like the number that you put the substituent on.
Yes, so because butyl comes first alphabetically, we want that to be our number 1.
Oh, okay. Thank you.
Yep. All right. So we have a ring and a carbon chain. Our ring has 3 carbons in it, and our chain has 4, okay? So our parent chain is going to be the chain, okay? The parent group is going to be the chain. So we have 1, 2, 3, 4. Our substituent is off carbon number 1. Okay, that's why I numbered it that way. Okay, what is our substituent? How are we going to call it? It's a ring, so it's going to be what? Cyclopropane. Okay. Okay. Sorry, did you say propyl?
Yeah.
That's exactly right, because it's a substituent. Okay. We know that it's going to be cyclopropyl. Okay. It's on number 1, so we can write 1 cyclopropyl, but it's not necessary. Okay. Cyclopropyl, and then what's our parent chain?
Butane.
Butane. Perfect. Okay. Cyclopropyl butane. That's how you name that one. Does that make sense to everybody?
Mm-hmm.
Perfect. All right, last one, everyone. We're almost there. Okay. So let's number our longest chain. 1, 2, 3, 4, 5, 6. Interestingly, we have a ring that is the same. So which one is going to be our parent chain? The ring or the chain?
Not sure.
Okay, does anyone know?
I say the ring because it has substituents off of both ends.
Perfect. And the other way to know that is a ring takes priority over a chain if they're the same number. Okay. But yeah, you're right. You wouldn't be able to name this as a substituent because you don't know how to name that with the two methyls off of it as well. Okay. But just know if the chain and the ring are the same, the ring will take priority. Okay. So now we need to determine what is the name of this group. How are we going to name that? Six carbons gives us what?
Hexyl.
Hexyl, okay. Hexyl, okay, it's like hexane, but because it's a substituent, it's going to be hexyl. And then we have dimethyl. Okay, and we're going to do the difference between H and M. So which one comes alphabetically first?
H.
So I did number that correctly, that we put the number 1 with the hexyl group, but I did not number it correctly in the direction we went. Okay, so we're going to want to go this way because that gives our methyls the lowest number possible. Perfect. Yeah, you had it right. Perfect. Okay, so now we're going to name this. We've got hexyl, right? What's next?
3,3.
3,3 dimethyl. Our parent chain, our parent ring.
Cyclohexane.
Cyclohexane. Perfect. All right, and that is the end. Oops. All right, so let me go back to this, stop share. All right, does anyone have any other questions on any of these topics? Let's see, there was a question. You can't just put 3-dimethyl. No, because there's 2, the rules are that you put 3,3-dimethyl. Seems redundant, I know. You'd think it would be like 3-dimethyl or 3,3-methyl, something like that, but for some reason they do both, 3,3-dimethyl. The reason for that is because if it was at a different location, it would be like 3,6-dimethyl, something like that. Okay. So the rules remain the same even if they're on the same carbon. Awesome. Any other questions about anything coming up on exam 1? Any questions on homework? Anything I can help out with before we finish up?
This was a lot of help.
Good. I'm glad it helped. Good. I'll do these before each exam, and also I'll start having weekly office hours on Wednesday mornings at 9 as well. So will he give us the name and have us draw the structure? Potentially. Yep. He could give you the name of something and say what is the structure, but it's all going to be multiple choice. So shouldn't be too crazy difficult. Awesome. Any other questions? Great. Well, thanks for coming, everybody. I hope that this was helpful and that you learned a little bit. Again, your exam is on Thursday, so I'll be doing office hours on Wednesday, and one of the other TAs, Ashley, will be holding an exam review tomorrow from, I think, does anyone know, is it 5 to 7? Yes, 5 to 7. And I will work on getting the recording. It did record. I don't know where it recorded to or how that works. I'm going to have to go figure that out. But anyway, I will let you guys know as soon as I have access to that, and we'll post it if I can. Tomorrow's session will not be the same question. She's going to go over the practice exam that Dr. Garg posted. So give that a try and come with some questions there as well. Cool. Thanks for coming, everyone. I will see you on Wednesday.